Hello, let's talk about today's material. Today we will cover screen and workspaces, different spaces. So I wish that at the end of this class, I wish that you can understand the different spaces of the basic OpenGL command. And we will talk about this example or this visualizing Julia set to introduce those spaces. Also, before we talk about today's material, I'd like to briefly run over the main topic that we talked about last time. So I mentioned that last class I mentioned that these different student activities, including program assignment, video summary submission. I do not expect you to go over the paper, but basically you can very easily watch the video. So just go over the Figure Asia video, and then you can express your own opinions, and then submit it through the online submission site. Also, there are every week homeworks, like they're going off slide and coming up with some questions. Also, near the end of this semester, we will have this post presentation. So basically, that's why I asked you to look at this recent Figure Asia video, and then you can see some of recent technique, and then you can find the one paper that you can actually present the paper to us through this post presentation. Also, I talked about the grading policy. I strongly recommend you to watch the last video and then get a full understanding of the student activity. So basically, I'd like to talk about the basic basic OpenGL program. Basically, this actually when you actually when you run some of the basic OpenGL the command, you can actually get this kind of the screen. So basically, this 2D screen, the window is basically starting from the -1 to 1. Also, the y-axis also same thing, -1 to 1. So basically, here actually black screen with this kind of teapot in a wireframe. So you can also you can also draw this kind of rectangular shape with this OpenGL command. This kind of Lagos OpenGL command, but actually some of the recent techniques, actually some of recent OpenGL one is a little more complicated, but I actually they use this one mainly for this easier for the education purpose. So here you can see that we want to draw the rectangular shape, and then we specify the color GL. Every OpenGL command start with the GL color 3D. And then you can see that there are three parameters. You can see that it's actually the three indicating this. There could be the three parameters: RGB, red, green, blue, the color channel. And then also there are the four vertices: GL, vertex 2D. Actually, they're indicating that there are 2D coordinate. There are four vertex: 1, 2, 3, 4 vertex. And then I mentioned that the window OpenGL, the window has this kind of coordinate system: -1 to 1. And you can see that given the coordinate system, this -0.5 and -0.5 should be here, I guess, right? And then this one should be the x and this one, and this one should be here, and this one should be there, right? And then we specify four different vertices, and then we group them. We actually interpret those four vertices with the GL polygon. Actually, there are many unknown information here. I will talk about it here. So here actually there are D actually the suffix indicating this the 64-bit double. Basically, this actually double type, and then in OpenGL you can use this kind of one. So indicating there should be the three different parameters, and each parameter represented by the double. There could be the other one, the integer. Basically, if you know the C type is one, you can very easily understand what other these indicate. So I is the integer, something like that. And here you can see the GL color 3F. F is actually float here. This is also RGB. You can use you can specify this variable directly here. You can specify the constant value and pass them to the function. Also, you can create some sort of the buffer, array buffer here. Specify into this buffer, and then you can specify this the address, the pointer of this array. So typically it's actually much more efficient to use this buffer for drawing. mainly because once if we use this kind of buffer, we can send this data directly from the CPU side to GPU side, so that improves this actually the performance. Here's another example of this OpenGL. We draw this triangle, and you can see that it's color and the three vertex. Those three vertex should be indicating these three vertices. Also, we actually group them with the GL polygon. Now let's look at what this GL polygon means. There are actually many different drawing primitive in OpenGL. Basically, the GL polygon. Where's GL polygon? Here, this polygon. So basically, if we actually group call the vertices with the GL polygon, we ask the OpenGL to create this kind of polygon type. They're connecting V0, V1, V2, V3, V4, something like that. And another common, you can see that there are GL line loop. With these vertices, we actually make this kind of line loop. And also GL triangle. So for every three vertices, V0, V1, V2, we create one other triangle. For another three vertices, we create another one. So there could be the different primitive. Now we'd like to see here another example. Here actually we draw this circular circle here, and there could be many different way of drawing the circle. For this one type, here we specify the color again, and we actually specify we specify this vertex here under the circle here, and we group them with this GL line loop. Line loop, you can see that once we specify this vertex, we connect them with the lines actually. And here you can see that we approximate the circle with this 360 vertices, and we need to compute compute the coordinate of these vertices. So actually, the coordinate of these vertices comes with x and y, and then you can see that I is actually the degree, and then we convert them into the degree into the radian value, and we call this cosine sign. You might recall that the coordinate of circle can be represented by cosine theta and sine theta, and actually these are computing the coordinate from the angle. Actually, I is the degree, and then we call once we compute the coordinate, we call the GL vertex to the x, y, and we group them with the GL begin and end with this GL line loop. So OpenGL is kind of state machine. OpenGL maintain various state until you change them. So for example, here you actually set the color, right? Then all the other following vertices and actually affected by this GL color. Basically here you set the state color with this one, and then unless you change them, you apply this color again and again. And there could be actually many different state variables related to lighting and other one. So you can enable, disable those modes based on this GL enable and disable. You can see some example later on. And also you can ask the OpenGL what are the current states through this query state variable, this GL get float variable, and GL is enabled, something like that. Also you can even ask the OpenGL whether you got the error or not, like the GL get color, something like that. And actually this is actually one of very simple debugging tool. For example, sometimes actually you call some of the OpenGL function here. This actually this related to this texture mapping, and then sometimes there could be some error. Then I recommend you to use this kind of one check error with this text, and then basically this macro here. And then once you call this one, and then you first check that you ask the OpenGL whether you get the error, GL get error, and then if there's some error, then you print that error with the number. Basically, the GLU error string, instead given this error code, you actually creating the text message with on your actually this text in this case text. So you can see that some error actually happening with this at this stage or this stage. So here actually this very old OpenGL one, you can see that it's very easy to use. But if you see that some of the recent OpenGL one, it's very much more complicated. So I don't want to talk about this very low level detail to you. Instead, I'd like to talk about the more higher level concept, which will be much more important also will be the last in coming years. So some of the recent change along the computer graphics, the Vulkan library. This kind of actually as you can see that there are many different devices like the PC and mobile phone. Also there are many other recent IP devices, right? So we wanted to use the new library. They can once you program it with the OpenGL, you want to use that program across all these different libraries, right? With a very fast performance, right? So that's actually main need for the Vulkan. And then Vulkan actually provide a very direct GPU control, but actually they're for achieving the very high performance. For example, our mobile phone is slower than the PC in terms of performance, right? But the people want to play their game on the mobile phone. So we wanted to have the very first. It's very difficult to get very high performance on the mobile phone. That's one of the reasons why we use the Vulkan. Directly, they're controlling the GPU. We wanted to achieve the higher performance. But usually, higher performance require much more coding and much more the difficulty and with more low level knowledge. But that's why I wanted away from this kind of low level information. But still, if you are interested on this one, I recommend you to go over this one. But in this class, we are not going to cover this one. Again, so basically there are here I actually decided that there are a lot of technical development along the real-time rendering, but it actually adding more complexity require you to know the low-level details for high performance. So it's actually I think that it's makes you away from it actually makes difficult for you to enter this field. So also another trend is that the physical based rendering is actually getting more widely used. So I think that fully understanding main concept of related to this physical based rendering is much more important to know the very low level information. Still, if you're interested in know this kind of one, I recommend you to study by yourself. But in the class, we are not going to talk about that kind of low level one. So basically, given that context, we decided to use the Legacy OpenGL since it's very easy to use. I think that it's very good as a teaching tool. And we will talk about some of the current form to differentiate the new version and the recent one. Also, I will talk about I will point out the nature of the rapid evolution of computer graphics, the computer science. You can see that some of technology actually evolving, right? So depending on your niche, you can also follow that one, or you can look at some other directions. So also all the program assignment will be given by based on levels of OpenGL since it's much more easier than the recent one. Also, we'll talk about this one in the class. We'll talk about the basic one so that you can do your homework. We don't require you to know a lot of the OpenGL command and the advanced one. Instead, our main goal of this class is that we wanted to implement some core technology of the rendering and some of the what's going on under this OpenGL. And actually, this is a classical rendering pipeline. There's some of the implementing a lot of the main tools. So you know that there's CPU and GPU, right? The workload related to the graphics actually require a lot of computation overload. So that's why we usually have this kind of separate device called the graphical processing unit (GPU). And once you send this data from CPU to the GPU, we usually go through these main two steps. One is the transformation, which is more related to this vertex processing. And since you know that we will do a lot of transformation. Once we do transform this different triangle into the screen space, then you need to convert the triangle into the pixel level. In the end, you need to have this image, right? Image actually consists of this kind of pixel. First, given this triangle, we need to compute what are the actual pixels within that triangle, what are the color, right? That's typically known as rasterization. Typically, there are a lot of these OpenGL main designed to efficiently perform this transformation and rasterization process, and these are the two main steps of the rendering pipeline. But if you look at the recent OpenGL, actually program also there are much more complicated steps. Not just these two steps, but higher level actually. They're here actually more or less related to this vortex processing corresponding to this actually the transformation that I talked about here. That's why I said this. I mentioned this vortex processing, and then once you are done with some of the vortex level, and then once you are done with this rasterization, you can now see that actually these all those operations are related to this pixel level. So even though the recent one is much more complicated, the higher level they also consist of the vortex processing level, also pixel level processing. Also, there are many tools related to computer graphics. You might heard about this kind of the engine, Unreal Engine, Blender, Unity, and so on. These are the actually game rendering engine, also modeling animation tools. So there, for example, you can use Autodesk to design your character and use the Unreal Engine to render them. Also, there are another one, Vulkan, OpenGL, also the DirectX. They are actually more level rendering the rendering tools that are achieving their high performance. Also, they can, if you're using this kind of tool, you can also directly use the GPU so that you can get a very fast performance. Also, there are some other additional language like the shading language, so GLSL or the HLSL. But actually, we'll get back to that later on. What are the actual shading language? And shading is basically once you actually have the light source, you can create some sort of color on the object. That is known as shading, and that evolves into some sort of certain general program, even to this general purpose computing language on the utilizing GPU. You might heard about GPU, also CUDA. So now the GPU getting more flexible. Now you can even run the different program on the GPU. So it requires you to have the advanced general purpose language, not just this kind of the graphics specific language. So that's the reason why we actually CUDA from the NVIDIA. Also there are more other the corresponding language OpenGL. So these are some of the related tools and language, and then unfortunately we are not going to talk about a lot of the tools here, but we will mainly focus on the main rendering technology. So now I'd like to show some of very simple example. This actually Julia said it's here actually basically this visualization of the fractal. So it actually has a very interesting behavior, and then sometimes actually the fractal actually Julia said defined on the mathematical function, right? So it's very hard to understand that function, right? But once we can somehow visualize this function within the screen, it's basically it can give us the better intuition on the function, right? So let me play this demo. This is the actual OpenGL program, and here actually this some of the function we are somehow visualizing this Julia said. And if you click the left button, we are zooming in. You can see that if you keep zooming in, you can see the same pattern appearing again, right? This is actually an example of the fractal, right? I just got here. I recommend you to play this one. This is actually the link in our course homepage. The Julia set is to define something like this. Julia set J sub C for number C and in a complex plane is given by something like this. So we starting from the PI and we multiply with itself again, adding the DC. We make the next iteration, and we keep doing that. And if we convert to the fixed limit, then we said that it's in the Julia set. Otherwise, it's not in the Julia set, right? So I guess you understand this complex number that consists of the two tuples, real and imaginary. You can just in case actually I provide here the base operation on the complex number. And so, for example, the real number is subset of complex number, right? So let's see that in what cases some of this series will converge or not, right? For example, assuming here actually C is 0,0, then if we actually have if we have this initial number x of 0.5, if we keep doing this iteration, you can see that actually it will be converge, right, to some number, right? But if we had an initial number of 1.1, you will see that actually it will diverge, right? We can also think about it. We can actually generalize with this even for complex number. You will see that at this case c is 0. Then in the case of real number, the magnitude of x is bigger than 1. You know the series will diverge, right? And for complex number, this are will lose bound. Magnitude of your complex number becomes bigger than 2, and series will diverge actually. Computing actually type bound for this case is not really important in our course. So basically, we just utilize this property for creating our visualization. So in this case, actually actually this corresponding to the real part, and this corresponding to this imaginary part, and then the black point are the ones in the Julia set. I mean, basically the point within this one, the magnitude less than this one actually they actually converge, and then we assign them as a black color. But actually, what we are interested in is that the other numbers that are in not the Julia set, but actually we wanted to visualize it those regions. So these are actually some of the fractal chords. Here we define the actually complex consisting of the real part and imaginary part here, and that's a Julia set function. It starts with the P and C. And then in the end, we return we actually return I and R, this reference pointer. And then here, this actually iteration part, we study basically we keep performing the iteration. We multiply P and P plus C and make the next iteration. And then we wanted to see this magnitude, right? So if the R squared, it's bigger than 4, here actually magnitude 2, right? If we're taking the root, actually if the bigger than the 4, we break it out, and then we return, and then you see that actually we actually compute the I, we assign I with the number iteration until we break out this loop, and R is actually this magnitude of this value, right? But if we keep if the series is converged, then we keep iterating, and then probably I will be assigned with this next iteration, and at that time also we will get some very small this R value, I guess. So here we use the I and R actually as to assign a color. So the issue is that the Julia set is defined under this wide open space, right? Across the real and imaginary, right? But in the end, we need to visualize this function within this OpenGL screen, within our screen, right? But actually there is mismatch. You can see the world is very wide, it's unlimited, but our screen space is only limited. So we need to actually define a mapping from our wall to our screen space. That's why we need to have some sort of mapping space. So for example, that's the main reason why we wanted to have why we wanted to have this camera. We set the camera in the wall, and we want to look at the small part of the wall through this camera, and mapping that the image on top of let's say this monitor screen, this our window. So actually since our screen space is only limited, we only look at, you can see the region of the wall that's seen through this camera, and we map that here within this window screen. That's actually mapping from the wall to the screen. And screen space, you know the screen space consists of this pixel, right? And pixel is nothing but just 2D array, the buffer. And there could be many different conventions on the screen coordinate. For example, in some cases, the actual coordinate could be here, and increase y and the axis, right? But in the OpenGL screen coordinate, usually the OpenGL case that we actually the original coordinate is here typically, and then we increase x coordinate, and y coordinate. So you can see that actually there are different coordinate conventions. You need to aware of this one. This is more like purple level convention. This is more like the mathematical convention. And you can see that actually it's very clear that we need to have the world space, also this screen space. But in the middle, we also typically use this normalized device coordinate. It's more like intermediate random space. and between the world and screen space. This was known as canonical screen space. Basically, NDC actually introduced to simplify a lot of the random operation. You will see that later on by using this NDC, this canonical space, we can actually we can simplify a lot of operations. That's we are using this one. But by now you just assume that we are using the NDC in the middle of here, and this actually is a normalized device coordinate and starting from the -1 to 1. And our question is that in the example fractal case, we can actually find the world coordinate here. Let's say x w, but in the end we need to compute the screen space coordinate here, right? So let's say that's the x of s, and then also with from the world to screen space also we go through this NDC. So actually corresponding to xw, we can define the corresponding this coordinate, say xn. The question is that given this xw, what are the coordinate for xn and xs, something like that. So we actually here actually I overlapped these two screen space together here, and then in the world this screen space in the world case, let's say this the left one is we denote as the world dot L, this left, and this the right, and this world dot bottom and world dot top, and this actually starting from the -1 to 1 along x, and same thing for y. So for example, actually when I show this first OpenGL example here, see that I mentioned this one actually, right? I showed this one. This actually I'm just visualizing this space they're coming from the NDC. That's why actually it's starting from -1, starting from the -1 to 1. Let's get back to the okay, so now the contact, right? Then given this world coordinate, what are the actually corresponding NDC coordinate x of n? Then we can maintain this that we can actually given the same ratio. I mean for this point within the world space or the NDC space, the ratio between the world and screen space should be the same thing, right? In other words, let's say this the ratio between the ratio between this in the case of world, ratio between this the width, WR minus WL, this width between the ratio between here and then this one. So you can see that XW minus WL. Sorry about there's some missing the parentheses here. Should be maintained with even in the ND space, right? ND space the width is this one, right? 2, and then the ratio between this whole width and to that one should be something like this, right? This equation should be maintained within the world space of ND space. Base this one, then we can compute this x of n. Base this one. Overall, actually, starting from this world coordinate, we apply some a and adding some b, then we can compute this one. A and b actually represented by something like this. So bottom line is that starting from the world coordinate by multiplying some number, adding some number, we can actually get this one. Same thing from the NDs to the world screen space. Same approach, same ratio of the one. Then we can compute this starting from the x of n. We can compute actually the coordinate in the screen space. Same starting from here, we can also compute this one. The issue is that we need to do this kind of the computation. It's a very simple computation, but we need to do this operation for every every vertex or even every pixel, right? It require, for example, if we actually have many vertices, like 1 million vertices or a lot of pixels, then it require basically a lot of computation, and it will take a lot of time. That is the main reason why we need to have the GPU to accelerate this process. Okay, so I wish that by now you can understand the different spaces and basic OpenGL command. And then I talked about the Julia set example. I talk more about how to implement Julia set the OpenGL programming here. But I wish that you can understand why we need to have the world space and screen space, NDC, and variable mapping between them. And also I mentioned that you need to come up with the questions and at least 2 times during the whole semester. And then I will actually look at the view question, and then basically I'd like to encourage you to come up with the questions, right? So to do that, that's why I have this homework. But don't worry about score, and most of them is actually, it's not already answered question. Actually, I will give you the one for the already answered questions, the common questions. I need to change this wording, and then I will give you the 2 for the question with the thought or some or question that surprised me. Sometimes I don't even know the answer of that question, right? Then I will give the 2. But actually, most of students, most of question will get the 1, right? So don't worry about the score. It's not a real big deal. But think about it. What are unclear part? How can we actually apply this technique to the other field, other related one? I will actually that's actually the main reason why I think this one. Also, sometimes actually some people didn't submit the question, and then near the semester, end of semester, they actually provided the multiplication. Don't do that actually. Multiplication in one time actually will be counted as a single time. And another one is that go over the next lecture slide before the class time, so that actually you can prepare this material. Also, again, watch the 2 figure-out-figuration video and submit your summary before the every Monday class, right? You can submit on through the online one, and then you can just provide just 1 paragraph by watching the video, and you can use the English and Korean. So, for example, if you go to the home page, so and you can see that actually the paper summary submission here, right? And below that actually you can see that this graphic collection, right? If you click this one, you can see that a lot of this SIGGRAPH and SIGGRAPH Asia papers. If you click this one, you can see that a lot of the SIGGRAPH papers here. You can actually you can click some of them here, this author version, and you can see that it comes with the paper and even the video. There's the video here. Then just watching this kind of video and then expressing your comments into the submission side. That's it. That's the requirement. Basically, the main reason why I have this one is that in the class one I will talk about this topic, but this one is more or less traditional. But a lot of the new things are going on under and a lot of new things usually appearing at the conference. That's why actually I'd like to give you the chance to look at what are the new things. Also, that way actually you can connect this kind of traditional stuff with this recent stuff. Okay, so these are another homework. Go over the chapter 1 and chapter 2 of my book, and then basically you can these books are already linked from the homepage. And then go over this one. So basically, the main reason why I said the homework, then it means that there will be the quiz next class time. Next time we'll talk about the basic OpenGL program structure and how to we'll see how the OpenGL supports these different spaces. Okay, that's it. Thank you. Bye.